In our previous video, we were talking about overfitting, and even before that, overfitting we saw in our forecasting models with our polynomials. We looked at, just go to the end of this data set here. When we fit a polynomial, for example, on our complaint data in a previous video, when we had a polynomial of order 4, we matched every movement of the data used to create the model. But then when we went and looked at, in this case, forecasting ahead in the future, the model went straight up or straight down, and so it was a terrible predictor of that future information. Even though it really fit really well, the data used to create the model. So this is the idea of overfitting. Now, if you have overfitting in your time series data with your polynomial, the solution is to reduce the number of orders, have less complicated polynomial, so maybe just a polynomial of degree 2, so it just goes up and then down, or use a linear regression, smooth it out, rather than have a polynomial of degree 4, 5, 6, whatever you got. Well, when we are doing multivariable regression, we have many different predictor variables that we are using. And if we're doing linear regression, where we're trying to predict a number that is continuous, so it can have fractions, we do have to be concerned that we have lots of variables to try to predict the data, but we could be overfitting the model in terms of it has high accuracy for the data we built the model on and not so much for future data. So there were two ways to kind of deal with this for linear regression. We could do ridge regression, which minimizes the impact of the predictor variables by making the coefficients slightly smaller so you can keep all the different variables in your model. Or we have lasso regression, which adjust for the overfitting by making more of the coefficients 0. And this is used when you have predictor variables that might have limited information. So for example, if we have a predictor variable that is a measurement and the majority of our data doesn't have that characteristic at all, so its measurement is 0, or whether it is a categorical variable where only a small number are in that particular group. So in that case, we're getting less information from these variables to help us predict. And so if we're getting less information from these variables, the lasso regression model makes more of the coefficients in front of those predictor variables 0. So essentially just removing some of the predictor variables. Okay, so let's take a look at how this lasso regression would work. And so we are working in this particular data set here at drstephpowers.github.io/BIA. We are here in this one called regression. Okay, and we are using the data set that you will find by clicking in here. We're using this data set, just to go back in time here, that we used in the linear regression video, where we are trying to predict the earnings per share. And we're using this New York Stock Exchange data set. So just to go back, that we put into our Google Drive, we have read it in using a CSV. So we've called it stock. We've taken a subset of that data set. So we're just focusing on cash ratio, after-tax return on equity, gross margin, and current ratio to predict earnings per share. We then used our X-train or our test train splitter here to split out and create that training data and that testing data. We're testing 20% and training 80%. Previously, we looked at a linear regression model with this particular data set. What we found is that it doesn't fit particularly well. That when we looked at the variables here, they were 3 out of the 4 were statistically significant, but that the R-squared was very small. Okay, so we're not explaining all of the different variability in the earnings per share. Okay. Now, we would use ridge and lasso regression if we had a much higher R-squared and probably a lot more variables to help then in terms of that overfitting issue. Here, we're going to use it with this particular data set. We found the ridge regression really didn't have much of an impact because it really wasn't an overfit model to start with. But I will show you here how the lasso regression impacts this particular data set. Now, when you do lasso regression, we're doing it from sklearn.linear_model. We're importing lasso. Lasso has a hyperparameter of alpha, and this is going to be how much the so remember, with lasso, what we're doing is we're making more of the coefficients 0. And so here we're looking at how much of the variance of the estimates. That's not right. So the lasso, just like alpha, has this alpha hyperparameter. And this alpha hyperparameter is how much the variance of the estimates are reduced. It's just using a different method to do that. So remember, the ridge was minimizing the impact of the predictor variables by making the coefficients smaller. With lasso, it's making more of the coefficients 0. So it's attempting to achieve the same thing, but with a different approach. So from sklearn.linear_model, import lasso. Let's start with a lasso of alpha equals 2. We're going to use the same training data that we had previously. So this is from the New York Stock Exchange data. Sorry, I'm just going to go back in time here. So we had stock, we read the CSV file from our Google Drive, we looked at this data here, we're trying to predict the earnings per share. We took a number of these ratios here, like the cash ratio, after-tax return on equity, to help us predict. And in a previous video, we created a subset where it was just that particular data, and then that way we could drop the NAs without losing additional sample size because there may be missing information in other columns that we aren't using. So we created a subset here, we dropped the NAs, we split it into test and training data. We have since then looked at the linear regression, and we have looked at it with ridge. So let's just look at it here with lasso, using that same data here, X train, Y train. And then from there, we can do is we can then call the coefficients. And what we notice, that's the ridge one. Let's go to lasso. All right, so we're going to fit our lasso, and then we will call the coefficients here and the intercept. Okay, so what you can see here already is that it has made, with our alpha equals 2, it has changed the coefficients in this case and dropped the last variable. So if we go back and look at, I hate scrolling back and forth, our data that we had, the fourth variable, actually let's just look at it here with this. The fourth variable, that current ratio, it has dropped that one from the model by essentially making that coefficient that you see here, a 0.0119, it has made that 0. And when it has done that, what it does is it does change the other coefficients. So here were the coefficients under ridge, 0.004, 0.0016, 0.01. And so we can see with our lasso here that these numbers have changed as well. So it's simplifying the model by making more of the coefficients 0. And that was with an alpha equals 2. So let's check and see how well that does in terms of predicting. So we have here our test data. We'll calculate the mean square error, 14.96, which is the same as the previous ones, 14.96. Okay. And we can look at our score here, 0.0079, R squared. So you can see the score is improving. When we look at these are all kind of versions of R squared. You can see that one negative, and go back to the other R squared here was also, there we go. So you can see that it is improving our model here. Simplifying our model, not increasing the error, giving us a little bit more accuracy here. And the accuracy here, this is with regard to the testing data. That's the ridge. So you have the training data and you have the testing data. The whole point here is to improve the accuracy of the testing data because you added all these variables because of the training data. Now what we want to do is figure out how to improve it on the testing data. So let's do here, test, okay. And so what we saw here is the score, right? We're still not very high on that test data. We can look at the errors. You'll notice the errors are very similar. We are looking for it around 0. Again, we've talked in these previous videos about there's this outlier here we need to address. Now, when it comes at alpha, we chose an alpha equals 2. You could choose a different alpha. We can actually use something called Lasso CV to actually find the alpha for us. So if we use Lasso CV, it'll find the best hyperparameter for us. And so CV being cross-validation. And what you're doing here with this cross-validation equals 5 is it's taking your data set that you have identified as a testing data set, and it's dividing it up into 5. And then what it's doing is it's taking 20% as the kind of test to see how well the model fits. And then it repeats it with a different 20%. And so it's going through and checking to see how much the model changes when you change what of the data is in the testing and the training data to find that optimal alpha. And then we're going to fit it here with the training data. Notice when we do this, what we get here is that if we change the alpha, even more of these variables have coefficients that turn into 0. And so it's basically removing a number of these variables, and it's only really keeping the second one. What was the second one here? It's really just keeping here this after-tax return on equity. Notice in the original version of our linear regression, that was the one that was not statistically significant, likely because there's high correlation, as we talked about before, between these different variables. When you calculate these things, they are using the same financial stats to do it, so there is high correlation between them, which is why when you even have 4 variables, we're still not explaining a lot of the data. So what it's done in the Lasso regression is it's removed the cash ratio, the gross margin, and the current ratio, and it's saying if you just got rid of those and kept the after-tax return on equity, you really are explaining a lot of the variability because there's a correlation between these, and so you don't really need that combination of variables. So it is actually reducing it down to just this one here. So what we can do is we can see from this that we can simplify the model to just that one variable. So in this case, if we did that, if we got rid of all these other variables and just kept the one, then when you look at this predictor and we compare it to the test data, notice that the mean square error is not any worse. So getting rid of those other variables, we haven't increased the size of the error. And we can check the score both on the training data and the testing data to see if those scores have improved. All right, so given all this information about ridge and lasso and linear regression, can you create, I can't even spell, can you create a better fitting model to predict the earnings per share? Can you identify appropriate variables and can you use the ridge and lasso regression to help you address perhaps the overfitting? Before we leave the topic altogether of this linear regression, let's just talk about how we would assess regression models. We did talk in a previous video about how you can look at the error, and we can call it residuals, we can call it measurement error, we can call it loss function, cost function. Those terms are all interchangeable. We've been looking at mean squared error, and we looked at mean squared error in forecasting as well. We're going to be using that mean squared error again when we get to neural networks. And there is another way to assess regression models. You can look at root mean squared error, which is the square root of the mean square error. Again, the average error should be 0, and we're looking at how much variability there is in that measurement error, either by looking at the average error or the square root of it. And we look at the square root of it because it comes back to the empirical rule. The empirical rule being that here in the center, we have our mean, and within 1 standard deviation is 68% of the data if it's normally distributed. Within 2 standard deviations, it's 95%. Within 3 standard deviations, it's 99.7%. So when we look at the root mean squared error, it's like looking at the standard deviation. If the error is at 0, we can look at how the error spreads from that average. It should be centered on the average, and we said that the error should be random around it, and it should be closer to that 0, and there should be less the further away you get. Now, we have looked at other ways to assess regression models. We've looked at R-squared, adjusted R-squared. There's different versions of R-squared depending on if you're looking at like a ridge score, a lasso score. Poisson has its own kind of version of R-squared. It's all looking at the same thing. How much of the variability in the data is explained by the model? And then we also have, we did some of that cross-validation. We look at the score related to that, which looks at in terms of if we change the data that we're using to build the model, how much does it change the explanation? And so higher scores there. So there are a number of ways to assess the regression model, more than we've looked at in these last couple of videos. Just as we leave the topic of regression, we've been looking at multiple variable regression, where we have more than one predictor variable. There is also what is called multivariate regression. This is where you have more than one outcome variable. So here are the dependent variables. There's more than one. So for example, we could look at here if we're trying to predict math scores and English scores. Think about this as two columns in a table. And you're trying to predict both the math scores and the English scores with a model where we have attendance, IQ score, and income. And the idea here is that we'll have different attendance for the two, we'll have different attendance, different IQ score, different income. That will then impact the math and English scores. So the impact these have can be different to help predict the difference between the math score and the English score, but it's the same variables using to predict them both. We're not going to do the multivariate regression here. We'll stick to our multiple variable regression because we'll use that as we move into our neural networks.